Hello friends, from this class we will start studying about electromagnetic circuits and also how that circuits are made. A material which possesses magnetic properties is called a magnet. The phenomenon by which this attraction takes place is called magnetism. Magnets. There are two types of magnets. One is permanent magnet and the other is electromagnets or temporary magnets. Permanent magnets are mostly alloy or pure form of iron, steel or cobalt and nickel, which are either man-made or naturally occurring. Electromagnets are made by winding a conductor around a ferromagnetic material. Normally that will not be having any magnetic properties, but while we are passing current through this coil, it becomes magnets. Here these are the magnetic field lines, which is from north to south pole. Permanent magnets are used in audio speakers, microphones, etc. In this, the reaction between this permanent magnet and a coil inside this, see like this, here one permanent magnet is there and a coil is wound around it, which is moving. Similarly, in a speaker, one permanent magnet will be there and a coil will be there. How the audio output is produced, etc. we will be studying in later classes. A magnetic field is created around a bar magnet. Figure shows the magnetic lines of force around a bar magnet. Magnetic field experiences a nature of attracting particles like iron, etc. See here, lines of force are starting from north pole towards south pole. Inside the magnet, the lines are from south pole to north pole. Magnetic field is the portion where the field of magnetism is experienced. That is, when we are bringing a magnetic material, it will be having the force of this magnet in these areas, while here it will not be there. So it is the portion where the field of magnetism is experienced. By convention, the direction of magnetic field is taken to be outwards from the north pole into the south pole of the magnet, while inside the magnet, its direction is from south pole to north pole. Disadvantages of permanent magnets are that its magnetic strength cannot be varied once it is magnetized. See this magnet and some iron particles here. This is a small magnet having a low magnetic strength. Even if it is brought near that iron particles, it attracts only a very few particles. On the other hand, see this magnet having some more magnetic strength. When we are bringing near that iron particles, it starts attracting from a long distance itself. That is, compared to this, the attraction of this is more. Here we can see that once magnetized, the strength of this magnet cannot be increased and the strength of this magnet cannot be decreased, while magnetic strength of an electromagnet can be increased or decreased as we need. Electromagnets are made by winding a conductor around a ferromagnetic material. Normally, that ferromagnet will not be having any magnetic properties, but when we pass current through that coil, it becomes magnet. To understand how that magnetic field is created around that current carrying conductor, we have to understand some more things. We have to see how to mark direction of current while that current is coming in one way and going in the other way. Suppose in this conductor, if that current is coming towards us, we will mark it with a circle with a dot inside it. See here, in this wire, current is coming towards us, so we will mark it like this. To remember this, consider an arrow which is coming towards us. When it is towards us, we will be seeing its front sharp point inside the circle. While current is going away from us, we have to mark it with a circle with a cross inside it. While in this case, current is going away from us, so we will mark it like this. To remember this, consider the arrow is going away from us, so that we will be seeing its backside having a cross shape. When current passes through a conductor, a circular magnetic field is formed around it. The magnitude of that magnetic field depends upon the value of current passing through it and the direction, that is clockwise or anti-clockwise, depends upon in which direction that current passes. Suppose in this wire current is going downwards, then the magnetic field will be clockwise. On the other hand, if the current is going upwards, the magnetic field will be in the opposite direction, that is anti-clockwise direction. To find the direction of that field, we have to use Maxwell's right-hand thumb rule or Cork screw rule. Maxwell's right-hand thumb rule. Maxwell's right-hand thumb rule states that if a straight conductor carrying current is held in the right hand such that the thumb is pointed in the direction of the current, then the direction in which your fingers encircle the wire is the direction of the magnetic lines of force around the wire. See here, current is going upwards in the direction of the thumb, so it will be in this direction, while here current is going downwards in the direction of this thumb, so it will be in anti-clockwise direction, just opposite to the other one. See, when the current is going downwards, the magnetic lines will be in the clockwise. To remember this, hold your thumb in the direction of this current, then the direction in which the other fingers are pointing will be the direction of the magnetic field. This is another view of the same conductor where current is going in this direction. That is, the thumb is in the direction of this current and the finger indicates the direction of magnetic field. While current is going upwards, the direction of the magnetic field also is reversed. That is, current is going upwards like this thumb, and these other fingers are indicating the direction of magnetic field lines. This is another view of it where the current is going upwards, that is in the direction of this thumb, while the flux is the direction of the fingers. Maxwell's cork screw rule. According to Maxwell's cork screw rule, if a right-handed screw is turned so that the screw moves in the same direction as the conventional current, sometimes the current might be in this direction or otherwise in this direction, then its direction of rotation, that is clockwise or anti-clockwise, will give direction of the magnetic field. See a screw. For the screw to go away from us, we have to rotate it clockwise. For the screw to come towards us, we have to rotate it anti-clockwise. That is, if that direction of that screw indicates the direction of current, then the direction in which we are rotating will give the direction of magnetic field. For the screw to be removed or taken upwards, we have to rotate it in anti-clockwise. That is, when current is towards us, magnetic lines are anti-clockwise. For the screw to go downwards, we have to rotate it clockwise. That is, when current is away from us, magnetic lines are clockwise. As per Maxwell's right-hand thumb rule or Maxwell's Cork screw rule, when current is going away from us, see the cross, that is, the current is going away from us, the magnetic field is in clockwise direction. And when current is coming towards us in this conductor, see that dot, that is, the current is coming towards us, the magnetic field is in anti-clockwise direction. See, in all these conductors going away, so that the magnetic field is in clockwise direction, while here current is coming towards us, so in all these conductors it is in anti-clockwise direction. When these conductors are brought somewhat nearby, the outer ring passes through the outer ring of the other conductor and it completes its cycle like this. Similarly here in the opposite direction. When it is brought further near, more lines pass like earlier, and finally when all these magnetic lines are completing its path like this, the passage of magnetic field will be in this way. That is, here it completes the whole conductors in clockwise direction, while here it is in the anti-clockwise direction. Now at the top we can see that magnetic lines are entering the inside the coil so that it becomes south pole, while here it is leaving and this end becomes the north pole. From the above explanation, it is understood how this electromagnet is formed. Next we will study some terms associated with magnetism. First one is magnetic flux, second magnetic circuit, third magnetic flux density B, fourth one magnetomotive force MMF, fifth one magnetic field intensity H, next absolute permeability or permeability denoted by mu, then comes relative permeability mu R, and reluctance denoted by the letter S. Magnetic flux. We know that when an EMF is applied across a load, a current flows through the circuit. See, here is a magnetic core wound with a magnetizing coil. When we pass current through this coil, magnetic field forms around the conductor, and when that magnetic field formed around each conductor gets together, so that magnetic field or magnetic flux lines are passing through the core. Magnetic flux is denoted by phi and its unit is Weber. Magnetic flux lines are just imaginary lines, while in an electric circuit, electrons are actually flowing through the circuit. The magnetic flux lines will never intersect. They form a closed loop. They behave like stretched elastic threads and always try to shorten themselves. Magnetic lines which are in the same direction and parallel will repel each other. North pole and north pole will repel each other. South pole and south pole will repel each other, while the magnetic flux lines in opposite direction will attract each other. Like electric circuit where current passes through a closed path. The closed path followed by the flux lines is called a magnetic circuit. See here, the total magnetic flux lines are passing from north pole to south pole. If phi is the flux and if A is the area of cross section, then magnetic flux density denoted by B is equal to phi by A, total flux divided by area of cross section. The unit of magnetic flux density is Weber per meter square or Tesla, Magnetomotive Force, or MMF. In an electric circuit, when electromotive force or EMF is applied, current flows as per the load. Similarly, magnetomotive force MMF is the force which establishes the magnetic flux in a magnetic circuit. In this core, we have wound a magnetizing coil. If a current I is passing through that coil, a magnetic field is set up around it, which in each turn gets added up and it flows through this magnetic core, or a magnetic flux is set up in the core. We know that magnetic flux is denoted by phi and its unit is Weber. If N is the number of turns of the coil and I is the current passing through the coil, magnetomotive force MMF denoted by F is equal to that number of turns N into value of current I. Its unit is ampere turns. Magnetic field intensity denoted by H is the magnetomotive force MMF per unit length of the magnetizing circuit. It is denoted by the letter H. That is, magnetic field intensity H is equal to magnetomotive force divided by length. That is F divided by length. We know that magnetomotive force F is equal to N into I. That is number of turns into current passing through that coil. From this equation, H is equal to N into I divided by L. Unit of magnetic field intensity is ampere turns per meter. It is also called magnetic strength or magnetizing force. From this equation 1, when L is brought here, H into L is equal to N into I, or N into I is equal to H into L. But we know that F is equal to N into I. That is, F is equal to N into I, that is equal to H into L. Absolute permeability or permeability. In electricity, the ability of a conductor to allow current to pass through it is called conductivity. Similarly, in magnetism, the ability of a material to allow magnetic flux to pass through it is called permeability of that material. It is represented by the letter mu. The flux and hence flux density B are directly proportional to the magnetizing force H. That is, B is proportional to H. Here the constant of proportionality is mu and its unit is Henry per meter. Therefore, this becomes B is equal to mu into H, or mu is equal to B divided by H. Absolute permeability of free space or air is denoted by mu 0 is equal to 4 pi into 10 raised to minus 7 Henry per meter. Relative permeability. See, this is a magnetic circuit with one portion a ferromagnetic material and other portion vacuum. The ratio of flux density produced in a material to the flux density produced in vacuum by the same magnetizing force is called relative permeability. It is denoted by mu r. That is, mu r is equal to flux density B produced in a material divided by flux density B in vacuum. We know that B is equal to mu into H. So, flux density produced in a material is equal to mu into H, and flux density in vacuum is equal to mu 0. That is permeability of vacuum into H. Here, as H is a common factor, we can cancel H. So, this becomes mu by mu 0. In other words, relative permeability mu r is the ratio of permeability of a material mu to the permeability of free space mu 0. When this mu 0 is brought here, mu is equal to mu 0 into mu r. As B is equal to mu into H, flux density of that material is equal to mu 0 mu r into H. Reluctance. We know that resistance R of a material is its property to oppose flow of current through it. Similarly, reluctance denoted by S of a material is its property of opposing the creation of magnetic flux in it. In an electric circuit, resistance R is directly proportional to the length L and inversely proportional to the area of cross section A. Similarly, reluctance S is directly proportional to the length L and inversely proportional to the area of cross section A of the magnetic path. That is, resistance R is proportional to L by A. Here, reluctance S is proportional to L by A. Here, conductivity mho is the constant of proportionality, so that R is equal to L by mho into A. Mho is conductivity. It is called mho or sigma. In the case of magnetism, mu is the permeability, which is constant of proportionality. So, this equation becomes S is equal to L by mu into A. Therefore, reluctance S is equal to L by, we know that mu is equal to mu 0 into mu r into A, where L is the mean length of magnetic circuit in meter, A is the area of cross section of magnetic circuit in meter square, mu 0 is the permeability of free space, that is 4 pi into 10 raised to minus 7, and mu r is the relative permeability of magnetic material. Thus, reluctance depends on physical dimensions of the material of the magnetic circuit. In an electric circuit, resistance R is equal to EMF E divided by current I, that is, R is equal to E by I. In a magnetic circuit, reluctance S is equal to mmf F divided by phi, that is, this S is equal to mmf F divided by phi. Therefore, this F is equal to S into phi, that is, Magnetomotive force F is equal to reluctance S into flux phi. So, we have said earlier that reluctance S is equal to Magnetomotive force F divided by phi, but F is equal to N into I divided by phi. This is equal to H into L, as we have studied earlier that F is equal to N into I, that is equal to H into L. From here, F is equal to H into L, and we know that B is equal to mu into H. From this formula, H is equal to B by mu. Substituting the value of this H here, F is equal to H into L becomes F is equal to B by mu into L, that is, B by mu 0 mu r, as mu is equal to mu 0 into mu r, that is equal to phi by A, because B is equal to phi by A into this L by mu 0 into mu r. So, okay friends, I think this video also might have been very simple and useful to you. If so, please like it, share it and subscribe it. Thank you. See you in the next video. Bye.